Alrighty, it is 1:15, and I think we're going to go ahead and get started here. So welcome to Intro to Sensors and Control. And in this presentation, we're going to go over some of the sensors that are available to you in VRC, and we're going to look at what kind of uses you can use for them. All right. So first, a little bit about myself. My name is Charles Jeffries. I've been involved in Vex Robotics for 10 years now. I did 5 years in in the VRC high school competition under Team 214B and 214V. And this is my 5th year in the Vex U competition on Team Pyro. And you can see a picture of us over there in the bottom right hand corner. I've also been volunteering in VRC for about 6 years now. Been head reffing competitions, some of the state championships. Some of you all might have seen me around as a referee. I often wear the blue flag hat. I am currently pursuing a software engineering master's degree at Arizona State University. And previously, I've worked as an intern at Optum, Garmin, and State Farm as software development internships. So I've been doing some programming for a while. All right. So one of the first thing that we wanted to do when we're talking about sensors is put them into different classes. And the classes depend basically on what it is that you're trying to sense. Do you want to know the rotation of a shaft or of a wheel or of a mechanism? Then in that case, we can use a potentiometer or some of the other sensors in that leftmost category there. In the second from the left category there, we can sense things like from contact. So for instance, if we have a lift that goes all the way down, we want to detect when that happens. We can use contact sensors. There's also distance sensors, which allow us to tell distance between the sensor itself and an object. There's a some visual sensors which tell us things like color or shape or position of an object. And then there's inertial sensors which do things with the robot's orientation or acceleration in lateral movements. And again, if you have any questions before we really get into it, if you have any questions, please put them in the chat or on the onlinequestions.org. I believe that number has been given out, but either way, I'll see it, whether it's in the chat or whether it's there. Right. So first, let's look at the potentiometer. Potentiometer is a rotation sensing sensor, and there are two versions available. There is the old version there in the upper right hand corner, which is the old V1 potentiometer. And it had hard stops on the ends of its rotation, which if you over rotate it, so say you accidentally put on a motor that would rotate continuously, it could break the potentiometer. So the way the potentiometer works is that it measures the resistance of a piece of metal as it's turned, and as the position on the metal is changes, the resistance changes. So in that sense, it's an analog sensor, which means that it uses the three-wire ports. It does not use those smart ports on the brain. It only uses the three-wire ports. Um, for It's generally used when you need absolute position. Because it's measuring resistance, it doesn't need to be reset. Um, it will hold its value when you turn it off, when you turn it back on, which is really useful if, say, you have an arm that you just want to know the angle of constantly. You don't want to have to re-zero it every time you turn on your robot or something like that. One note, though, is that especially for the old V1 potentiometer, if you swap it out with another one, the values for the same position aren't going to be quite the same. So you're definitely going to want to make sure you check your code every time you swap those out. Um, and the V1 also has a 250-degree range, which is enough for a lot of things like arms and stuff like that. But if you have something that rotates a lot more, it's going to be a little bit of an issue. The V2 potentiometer is new, and it came out, I believe, last year. It's in the bottom right-hand corner there. It has a bit of a different mounting mechanism. It has a larger measurement range of 330 to 3 degrees, which is significantly better. I know in my use cases of a potentiometer, that certainly would have been nice to have. And it has the ability to rotate continuously without breaking, um, which is really, really nice. I've broken too many to count of the V1 potentiometers in my time. the V2 potentiometer is definitely a lot more robust. That being said, if you have the V1 potentiometer, it's still a good sensor, and I wouldn't necessarily throw them all out and go buy V2s. All right, encoders. So whereas a potentiometer measures absolute position over a limited range, encoders can measure relative position from a starting value from when they started up over a continuous range, which means that you can have them rotate many revolutions. So, for instance, you'll oftentimes use encoders on drive wheels, maybe sometimes on the motor on an arm, which will rotate multiple times to go up or down, and such things as flywheels. Although we're probably not super many flywheels this year, but especially last year, being able to measure the rotational velocity of your flywheel was very useful. Um, the motors themselves, the V5 smart motors, both the large 11-watt ones here in this picture and the small 5.5-watt motors, both have built-in encoders, which you can see in that bottom right-hand corner picture there. You can see a black disc on the white shaft. That disc is the encoder. Now, the interesting thing is that that encoder is there before it goes into the gear cartridge, which means that the number of ticks that you have, the resolution of the encoder, that is the minimum angle that it can measure the difference between, will change depending on what gear cartridge you have in the motor. So, for instance, if you have a red cartridge, it's going to be able to measure all the way down to 0.33 degrees of movement. Whereas if you have a blue cartridge, it's going to go, your resolution decreases to 1.2 degrees. Now, the red quadrature encoders up there in the upper right is a little bit of an older sensor, but they're still pretty common. They're still a good sensor. They can measure 1 degree accuracy as long as you have both of those wires plugged in. And it's also a pretty good option. Now, there is one more continuous rotation sensor, which is kind of a hybrid between what you would think of as a potentiometer and a encoder, and that is the rotation sensor. The rotation sensor is a new-ish sensor that came out from Vex. I think it came out a couple of years ago, and it has very good resolution. So all the way down to 0.88 resolution. Remember that even the motor encoders on the motors only had up to the best resolution they had was 0.33 degrees. So this is 0.088 degrees, which is very nice. Um, it also has absolute positioning, very similar to how a potentiometer would work in code, where even if you turn it off and turn it back on, it will know its absolute position where it is within one rotation. It won't know how many times it's spun, but it will know where within a circle it is pointing. But that being said, it also can count absolute rotations. So overall, it is the best rotation sensor that Vex sells. However, from a cost perspective, there might be scenarios where it makes more sense to get, say, a few more quadrature encoders or just use motor encoders or something like that. It also does use up a smart port, which is not too big of a deal for VRC. However, this year with the higher motor limit, if you swap out those 11-watt motors for 5.5-watt motors, you might start to run out of smart ports if you have a bunch of rotation sensors. The other benefit of rotation sensors is it does have a high strength shaft input. None of the other encoders do that. So if you have, say, on your drivetrain or on a really heavy lift, then and you're using a high strength shaft, this is kind of your only option for directly measuring that rotation. Great. So here's like an example application for a lot of these rotation sensors. For instance, when your robot is driving autonomously, you might notice that it might kind of turn to one direction or the other or curve. And a lot of that is often due to sometimes small differences in frictions, differences in the variance between the motors of the left and right hand side. But when you're driving, but this is all an issue because in autonomous, we want to drive straight. We want to drive very defined lines so that our autonomous is consistent. So what can we do? We can use encoders to measure how far each side of the drivetrain has spun. So, for instance, we could put an encoder on a wheel. We can use the encoders even built into the motors to detect how far a wheel has spun. And if we know the circumference of the wheel, we can use that to calculate how far that side of the drivetrain has traveled. And from that, we can either, you know, just make sure that both ends of the drivetrain end up going the same distance, or we can even do more advanced closed loop control, which we'll talk about later, to make sure that the lagging behind side is sped up a little bit in order to make sure that we drive straight. Another tip here is if you're trying to use encoders on your drivetrain and you want to measure how far your drivetrain has moved, um, especially if you're going to be accelerating hard or having a pretty fast moving autonomous period as we do in VRC, then idle encoder wheels might be something you want to consider. So idle encoder wheels are wheels on your drivetrain that don't propel your robot forward, that don't really support the robot. The only purpose of those wheels is to not be powered by motor and to be spun by the ground as the robot moves over the ground. And then you have an encoder or rotation sensor or whatever measure the rotation of that wheel over time. What that allows you to do is when you are accelerating with motors in your drivetrain, especially with modern fast drivetrains with light robots, oftentimes your wheels, especially at the beginning of acceleration, will slip on the ground a little bit. And when they slip on the ground, that means they're rotating without the robot actually moving, which can introduce an error in our measurement for if we're, say, taking the rotation of the wheel and converting that into linear robot distance. So having a separate little pod, a separate wheel who is not driven by a motor and is only spun by the robot moving over the ground and is like rubber banded into the ground. So even if the robot like lifts up a little bit, it'll still be touching the ground. That is a very consistent way to measure our robot's position. And especially if you're going to go after more advanced control methods such as odometry and stuff like that, you're going to want some kind of idle encoder wheels for those measurements. All right, so moving on to contact sensors. There are two contact sensors really in the VEX system. There is the they're both kind of older sensors, but they're both still they're still valid. There's the limit switch, which is in the upper right hand corner here. It has a piece of metal that you can kind of bend to fine tune the activation point, how far away an object is before it triggers it. And then there's also the bumper switch. The bumper switch is not really recommended. It has some durability issues and sometimes it can be unreliable when triggering. I have personally seen teams use the bumper switch, for instance, to detect when a lift is all the way down in competition. And even though it comes down and smashes the button and it should close the circuit, it doesn't. And they end up with their robot stuck in autonomous or something like that because it thinks that the lift isn't all the way down. So for most scenarios, I would recommend using the limit switch unless you absolutely have to use the bumper switch. Now, there is the other downside is that the limit switch, that little piece of metal, it can be broken, so you want to be careful with it. But as long as you treat it nicely and are very careful, I've found that the limit switch can be pretty reliable and can last a long time. So one example that we can go through for this season is detecting when a tri-ball has been intaked. We don't want to intake more than one tri-ball to avoid violating the possession limit. So, for instance, we can intake one tri-ball, have that tri-ball push down a limit switch, and then we can stop our intake from moving. So that way we don't violate the possession limit. For instance, it could also be used to say we have some kind of catapult mechanism that's launching the tri-ball across the field. We can use that trigger to tell our shooting mechanism to start, say, preparing to launch a ball. Like if it's a catapult, start winding up. Yeah. The ultrasonic sensor is a type of distance sensor. The way it works is by you sending out a sound pulse, and then it listens for the reflected sound off of especially flat objects. And then because it knows the speed of sound, at least approximately, it can use that combined with the time to calculate the distance between it and the object that reflected the sound. Unfortunately, it's not super reliable. It's not really recommended personally because if you have multiple of these, they can start to interfere with each other. And especially if your opponent has ultrasonic sensors of their own, then it can start to interfere. That being said, I haven't seen too many of these around, so you might be fine, but you are kind of rolling that dice that you're hoping your opponent doesn't have their own ultrasonic sensor. Now, the alternative, it's a little bit more expensive, but it is definitely new and it is a lot more reliable, is the V5 distance sensor. The V5 distance sensor is light based rather than sound based, which means the possibility of interference with other things is a lot lower. And it basically is kind of used in the same way as an ultrasonic sensor. Um, the only other issue with it is that if you have a transparent object, so for instance, on the older field perimeter, if you use a V5 distance sensor with really clean plastic, it might be looking through that plastic and might give you inconsistent values. So whatever object that you're using against, I would recommend making sure that object is opaque. So either the metal on the perimeter or like a game object or a game element or something like that. The other neat thing about this distance sensor is that it has a really narrow range, and in that meaning that like the spread of the beam is very narrow. So oftentimes with the ultrasonic sensor, because the sound spreads out, it will catch a some object that's on the edge that's over to the side, and that it might measure the distance to that rather than the object that's right in front of you. The V5 distance sensor is a lot more, or is a lot better at measuring the distance to something that's directly in front of you. So yeah, example application would be measuring distance to a wall. Um, say we're an autonomous and maybe we drove over the bar, maybe we hit an object, maybe we hit another robot. We want to make sure that we know where we're at. So we can use the distance sensor to measure our distance to the field perimeter or to a tri-ball or to a goal or whatever it is. We can use our that sensor to know the distance pretty precisely. And if I remember correctly, yeah, the precision, it's basically plus or minus 15 millimeters. So it's not perfect, but that is a lot better resolution than you would get with the ultrasonic sensor. And we can even do things like instead of having to physically push our robot against the wall to reset its position to a known value, we can just measure the distance and use that mathematically. The line tracker is one of the older optical sensors. It's a three-wire sensor. What it does is it measures surface reflectivity, which is a bit unintuitive. So when you first look at it, it looks like it just measures light. There's not really something about reflectivity. But what you actually can't see is that behind that black square, which is an IR filter, is an infrared LED, which emits light that you can't see because it's infrared, which shines out of that port, hits an object, and then reflects back into the window. And the sensor then measures the amount of reflected light from that. Generally, this only really works for objects that are very close. So it's called a line tracker because there are tape lines in the field, and a lot of time, and back in the day, people would mount these underneath their robots, a fraction of an inch off the ground, and because the white tape would reflect the infrared light a lot better than, say, the gray tiles, they were able to detect the difference between a white tape line and a tile and just do things like follow that tape. That is definitely something that you can do. Still, we still have those tape lines, but I've seen it's a lot less common, especially with more modern mechanisms, more modern techniques like encoders and stuff like that. One other major caveat is because it's measuring infrared light, if there's lots of infrared light in the room that you're in, such as generally where I see this issue is from sunlight. If you have sunlight hitting the field and hitting the sensor, it can get really confused because sunlight has a lot of infrared light in it. So that is one major caveat that you want to be careful with using the line tracker. The optical sensor is kind of an alternative that's more modern and uses a smart port. It can actually detect the color of anything in front of it, and it has its own visible light sensor. So it's a lot more versatile. So not only can you detect brightness, you can detect color. This year, it's not quite as useful for like detecting the color of game objects, since game objects are for the most part all green, except for those colored ones. But those ones you would understand where they were in the first place. A lot of teams went to try and use this in changeup, where we had the red balls and the blue balls in order to automatically sort between them, and that's kind of an application that it's well suited for. Only downside is that the update rate, the rate at which the optical sensor is able to read the color of an object and report it is pretty slow. So it can only do it at 100 milliseconds per reading, which means about 10 times per second. That might sound pretty quick, but compared to most other sensors, like encoders especially, where they report their value every 10 milliseconds, so that's 100 times per second, this is a bit slow. Here's another. We can use these sensors to detect game objects in the intake in a different way. So, for instance, here we could use a limit switch to detect a tri-ball, which is in the intake. However, a tri-ball is kind of irregularly shaped. It's not a perfect sphere. So there might be orientations of the tri-ball where it might push the limit switch and where it might not push the limit switch. And unless you're going to somehow consistently have that tri-ball in a particular orientation, that could be a source of inconsistency in your autonomous routines. So uh, distance sensor, the optical sensor, or say a distance sensor even, can be used to detect when the ball is present by checking the color. So, for instance, here you can have a black background in your intake. The optical sensor will read black until the green ball moves in front of it, at which point it will move green. And at that point, you know the tri-ball is present in the intake, and that can be used to sense its position. Same deal with the line following sensor. The main issue being that you just need to make sure the ball gets pretty close to the sensor. So it can kind of have that same issue um, with the limit switch, where it can have inconsistency with distance. So the optical sensor is a pretty good option for this scenario. The distance sensor as well. Moving on to some of the more advanced sensors that VEX sells, there is the vision sensor. The vision sensor requires some extra effort. It is one of the more finicky sensors to use. There's been teams who have used it going back to its release in turning points, such as this robot here in the bottom right, which used it to aim at the flags that year. Um, the the way the vision sensor works is that it is essentially a small camera with an onboard processor where you program the camera to detect certain colors or certain combinations of colors. And then on that camera view, which is like a little screen essentially, if you can think about it, it will detect where the object is and how big it is as a square. It'll put a box around it. So in that scenario, you can kind of use it to find objects on the field. The issue is that it is very dependent on lighting conditions. So under different lighting conditions, different color lights, etc., colored objects like blue or red or green can look very different to the camera, and it might not be able to differentiate as well at different color temperatures. There can also be colors in the background. So, for instance, here, if you're looking for the blue tri-ball and someone on your opponent is wearing blue shoes or a blue shirt, that might be distracting for the vision sensor. It might start trying to drive towards your opponent's shoes. So there's a lot of work that has to go into making it viable and making it consistent. That being said, there are teams that have used it successfully. For instance, Arizona team 2647X in Tipping Point, so a couple years ago, used the vision sensor uh, in their world championship winning skills run, and they used that to detect the position of the goals, which might have been moved a little bit earlier on in the routine, and so they were able to get it to work consistently. So it's difficult, but it can be rewarding. This year, it could be useful during programming skills to find loose tri balls in the ground. If a tri ball started rolling around, if you shot one across the field, maybe it bounced, you can use this to kind of collect those extra tri balls. Okay. Moving into more of the inertial sensors, there are the yaw gyro and the three-axis accelerometer. These are old sensors. I'm not sure. It's probably been 4 years or so since these were really in use. Um, Ever since the inertial sensor, which we'll talk about in the next slide, came out, these have really fallen out of favor because their accuracy just isn't that high. That being said, if they're your only option, you can use them. The yaw rate gyro is a one-axis gyro that's analog. What it is able to do is able to measure how far it's been rotated from a starting point, from when it was powered on. This can be really useful for instance, to detecting how far your robot's turned and stuff like that, without being necessarily having to use encoders or some other method or even time. The issue is that it's old. It drifts a lot. It drifts a lot, meaning that even if it's just sitting still, it might start counting up on the angle, or if it gets hit, it'll kind of lose its angle that it had set, and the resolution of it isn't particularly good. It is only able to measure down to, I think, a single digit degrees, which is not particularly great. The three-axis accelerometer is another sensor. This one was used even less, to be honest. It measures linear acceleration. What that means is, as your robot moves in one direction or another in three axes, it can measure um, that acceleration. And because of that, it can be used to do things like measure when you bumped into a wall or when you bumped into another robot and detect things like unexpectedly running over something. But beyond that, it's not super useful. There are people who have attempted to use it to say, integrate turn the acceleration over time into velocity, and then turn the velocity over time into position. But realistically, within a few seconds, the value has drifted so far that it's not super useful. So it's not really, neither of these are really recommended. However, if they are your only option, there are some useful things that you can use them for. That being said, the V5 inertial sensor is probably, I'd argue, the single most valuable sensor that VEX sells currently. It provides three-axis angular measurement, which means that it can detect a robot rotating, a robot rolling, and a robot pitching up and down. And it is also a three-axis accelerometer. So basically, it combines the functionality of the previous two sensors we measured, and at the same time, it is way more accurate, way less prone to drift. It is really a great sensor. That being said, I'd still recommend attaching it to rubber links. And that is that little part in the bottom right hand corner there. If you mount that on there, it'll kind of absorb shocks, especially from getting hit by other robots hitting the wall, etc., which can help with drift. One thing to note about the inertial sensor is that there's a specific list of ways that you need to mount it. You can mount it in any one of these 6 orientations. And the axes will actually remain the same. So when it first starts up, it'll measure the position of gravity relative to itself, and will always make sure that Z points down towards gravity. Um, However, if the sensor is mounted at, say, like a 45-degree angle, it's not going to be able to measure gravity properly, and the values are going to be a bit off. Are going to be sorry, are going to be pretty off. So you want to make sure it's flat on one of its sides, whatever side that is. All right. So one application of this is we can use an inertial sensor as a more absolute measurement for turning. So for instance here, when we're turning our robot, we might get a small amount of error. We might turn a little bit too far, a little bit further than what we measured, or a little bit less than what we measured. So for instance here in this picture, the first image we turned too far in the first picture, sorry, in the first corner, and in the second corner we turned not enough to the right. And that can kind of cause our robot to end up in a different position from what we expected. So we can use an inertial sensor which keeps track of its rotation from when it was powered on, no matter what the robot's done in between, and use that to always make sure that we're facing the correct direction when we make turns. It also is helpful if we don't have idle encoder wheels at all, which would mean we'd have to use something like the motor encoders built in, which again is prone to wheel slip, as we mentioned earlier. That being said, it won't be able to maintain its position indefinitely. So for over the course of a 15-second autonomous period, the drift is generally not too bad. But for, say, longer periods like the minute programming skills, you might want to figure out some other options to determine your robot's heading. Or, say, periodically slam your robot into the wall, which will reset its heading to a known value, and then you can reset the value of the inertial sensor accordingly. So we've kind of touched on this a little bit. But I just kind of want to put together a list of what I would consider the key sensors for over under this year. Because a lot of the information that I talked about will be applicable for basically every season. But this season, there's a few sensors I wanted to talk about specifically. So the inertial sensor is basically always a must-have. If there's one sensor on this chart that you need to get, I would recommend getting that inertial sensor. It is the most valuable sensor here. It is very easy to get going to make consistent moves in autonomous, and it's just a good sensor. Encoders or rotation sensor would be the next thing on my list. Which, if you want to do anything with more advanced autonomous routines, you want to figure out where your robot is in the field. You want to very precisely measure how far it's moving to make sure that you're moving consistently. Then having encoders or rotation sensor to measure the rotation of your drive wheels is definitely essential. Um, the limit switch or distance sensor is also something that can be really useful for measuring to detect tri-balls in an intake. And like we said before, the tri-ball shape is irregular, so a limit switch might not be the best choice in this scenario, because a tri-ball might one time you intake it, it might be able to poke out and push the limit switch, but the next time it won't hit the limit switch. We want consistency. And then I would say, as an advanced use case, the vision sensor. The vision sensor is really the only sensor capable of doing what it does. It's the only sensor capable of detecting unknown state of the field. So, for instance, if a tri-ball is rolled to some place during your programming skills, and that's pretty chaotic. That's not something you're going to be able to predict exactly where a ball has rolled to. The vision sensor is going to be your only option to detect where that ball is and drive towards it, which, in my opinion, makes it potentially a key sensor for high scoring programming skills. So if you're planning on trying to win skills or get a good high programming skills score, the vision sensor might be something you want to look into. All right. So I just want to remind you guys, feel free to put questions in the chat or in the onlinequestions.org page. I will see either one. I'm going to take a drink here real quick, and then we'll continue on with some techniques for using the data from the sensors we collect. And if I see any questions, I'll stop and we'll address them. But otherwise, I think I'm going to go ahead and talk about using the data. So there are two general methods you can use to control a an effector. For instance, there is open loop control. Open loop control means that you send a control value to a motor. So, for instance, you're telling a motor to spin at a particular velocity or at a particular voltage or whatever. But we're telling it to do that, but we're not actually checking to see if the motor is moving as expected. So you can see at the bottom there, we're putting an input into some controller, some system we have for determining how the robot should move. And we're telling the robot to move, and we're just hoping it kind of does what we ask it. But say, what if for instance, that part of the robot is heavier because say we're carrying a ball, or say that side of the drivetrain has more friction, or our battery is a little bit lower than normal. Um, the motor is going to move slower than we expected, and we're not going to move as far. For consistency, this is bad. Um, this is and yeah, generally it's easy to implement. I mean, you can think about it. Just tell your motor spin at a particular velocity for a certain amount of time. But this does yield inconsistency. So if you're hoping to have a really high scoring, complex autonomous that can move all over the field, this is not really the way you want to go about things. Now, closed loop control basically uses that feedback from our sensors. So, for instance, if we have a sensor on the motor that measures how far the motor has spun or measures how far our drive wheel has spun, we can use that to inform our signal to the motor to tell it, to say move faster or slower or more or less. So, for instance, they say the motor spinning slower than expected, then we'll increase our voltage to make sure the motor spins faster to get to our target value. Or say it didn't spin quite as far as we expected, let's make it spin a little bit longer to compensate. And overall, this is much more able to compensate for differences in environment. Say you accidentally run over a tri-ball, say you bump into an opponent robot, or just say the field tiles are different at the state championship or at a tournament relative to what you practiced on at home. This kind of closed loop control can lead to a lot more consistency for that. Now, there's a lot of different ways to do closed loop control. I'm going to go over one algorithm here, which is pretty popular, especially in the VEX world, which is PID. PID stands for proportional, integral, and derivative. You don't really need to worry that much about what those words mean. I'll just explain their concepts. Oftentimes, a proportional controller is really only all you're gonna need, or a proportional and derivative controller, especially for say something like a drivetrain. What proportional, what the proportional part of the controller does is it tells the motor to move at a power that is proportional to the amount of error between the motor's current position and the target. So um, without P, we would kind of just send our motor at full throttle until we reach the value we want it to be, and then we'll tell it to stop. But this doesn't really work. For instance, you can think of driving a car and flooring the gas pedal all the way to a red light, and then the moment we hit the point on the road where we're supposed to stop for the red light, slamming on the brakes. This isn't really going to work. It's not going to be consistent, and you're going to end up skidding into the intersection, which, if you can think about it in terms of your robot's going to try and stop on the dime, but it's going to skid and stop a little bit later, which can lead to inconsistency. So, as far as proportional goes, what you do in a car is as you approach a stoplight, you will start to let off the gas. You'll start to slow down, and that's what proportional does. So as the distance between our position and the target gets less, our power that we give to the motor will become less. And that way we'll start to slow down. However, this doesn't really talk about applying the brakes yet. Applying the brakes is what derivative does. So you can see here on the bottom, on the right hand side here, that orange line is what happens if we only have a P controller. So you can see here we'll get to say zero power once we get to our target, which is labeled as set point here. But say you let off the gas pedal right as you cross into the intersection. Okay, well the car's not going to stop. You need to hit the brakes before you get to the intersection to slow things down enough. Derivative is a term that's designed to do just that. So it will reduce the amount of power depending on how fast you're moving, and it does that by calculating how fast the error is changing. So if the error is say 2 feet 1 second, one moment, and then 100 milliseconds later it's 1 foot. Okay, well now we know that we just moved 1 foot in 100 milliseconds, which is 10 feet per second. That's pretty quick. So if we keep on going at this speed, we're going to overshoot our target point. So let's reduce our drive power. This prevents us from overshooting our target and also prevents oscillation in our movements. This is very commonly used in drivetrain control, as I mentioned, as an example. Integral is a term that's less used in VEX. However, it's still very useful for when you need to get very precise movements. A lot of the time, this can be used in turn movements. You'll use integral to get that last fraction of a degree make sure you're very accurate. The issue being this. Because P only gives power proportional to our error, when our error is pretty small, say, going back to the car analogy, say we're only a few feet from the stop area, there's not going to be a lot of pressure going on the gas pedal, so the car might not really move. There's some minimum amount of power that we have to press in the gas pedal to get the car to move. The integral term will essentially apply a little bit of power over time when there's still some small error left. It will kind of accumulate more and more power until the robot starts to move. And once we get to that zero, it'll cut the power. So it's really useful for that last few feet, that last fraction of an inch, to make sure that our robot position is really, really consistent. Only downside is that it can take a bit of extra time to execute. So for really high speed autonomous routines, sometimes it's skipped. Right. So this is a video I found online. It is a really nice demonstration of what the different terms of PID do visually. So let's go ahead and play this here. So in this instance here, there's a motor controlling this arm, which is going to try and point to the center of the uh, graph here. So you can see the proportional control is getting it pretty close, but eventually, once we get pretty close to the set point, the the proportional control is no longer strong enough, and it's not able to get to the center. You can see here also that the proportional control sometimes can be too far and it can overshoot the stop. So yeah, you can see here now he increased P and it starts kind of oscillating back and forth, which is not something we want our robot to do. So now we're going to add some derivative and look at that. As we can approach the set point really quickly, but when we get in within a certain distance, we slow down pretty quick, which is great. So this is good enough for most drivetrain movements. However, as you can see, there's still a tiny bit of error left. Integral moves the needle the rest of that way. However, there are some tricky things with integral. So you can see how it overshot there. Now that's also because we don't have KD. So, but you can see over time, it will move the needle to perfectly in the middle. So you see that it does this overshoot. This is because there's a lot of tuning with these numbers. These numbers are going to be different for every robot. Oftentimes every autonomous routine, you're going to have to do a lot of your own tuning. There's a great document from a guy named George Gillard that goes over implementing PID in a VEX context, and I'll have that linked in these slides, which I believe will be sent out later. Let's see this one. Yeah, so there's also a couple other options. So for instance, there's a lot of different variations of PID. For instance, if you have a continuously rotating wheel like a flywheel or something else, there is an algorithm called take back half, which is kind of a modified P controller, which is able to tune some of those numbers itself essentially. Um, and I've personally used it to great effect for flywheels, and I found it that useful. This year, if there's probably not going to be too many flywheels, so take back half might not be super useful, but especially in future years, and especially last year, it was very useful. Um, that being said, there is a lot more out there other than just PID. PID is a very common one, but there are a lot of different options for closed loop control. Um, some are built on top of PID, more common ones. So, for instance, like drive straight control for driving a robot straight is going to actually have three PID loops in most circumstances. For instance, it'll have one PID loop for each side of the drive and then one to control turning. Um, that way you can drive straight at a particular velocity and everything is self-controlling. Um, and then there's also really advanced algorithms that can do things like tell your robot to move in a curve or to drive around objects or stuff like that. One of those algorithms is called pure pursuit. It allows you to essentially lay out a path for your robot to follow, and it will follow that path to the best of its ability. These algorithms oftentimes use PID loops within them to achieve their more complex behavior. Just some suggested resources, and these will be in the slides that will be sent out afterwards, I believe. These are some links. There is George Gillard's PID guide. I highly, highly, highly recommend anyone interested in more advanced VEX robotics, autonomous programming to read that document. It is a great explanation of PID. It goes into much more detail than I did just now with some really nice analogies. Um, it is the document that personally I learned PID first back all the way in, wow, 2016. It is a great document. There's also the link to that demonstration video we watched, and I also have a link for people who are interested in some of the higher level, more advanced algorithms like Pure Pursuit, which I linked to a forum article in the first robotics competition forum. All right. So that's the end of the presentation. And if anyone has any questions, I'll be here to answer them in the chat or on onlinequestions.org. Either way, I'll see it. And yeah, and then I think after that we'll be going into the intro to programming, which I believe is at 2:30. Sorry, it's actually the intro to programming will be at 2:45 p.m. All right, I don't think I'm seeing any questions. I will be teaching the intro to programming presentation on the same channel, on the same live stream. So if you come up with any questions in between now and then, feel free to put them in the chat, and I will take a look at them and give them an answer. But until then, until about 2:45 looks like, I think we're going to take a break, and I will see you all then. Alrighty, it is 2:45 here, and I think we're gonna get started here on Intro to Programming. So let's go ahead. So just to recap, if you guys weren't able to attend the previous presentation, I'll just go over who I am basically. So my name is Charles Jeffries. I've been involved in Vex Robotics for 10 years now, and I did 5 years in VRC under Team 214. Sometimes it was Team 214B, sometimes it was Team 214V. Um, I'm now on my 5th year in VexU on Team Pyro, and you have a picture of us down there in the right-hand corner. And this is also my 6th year of volunteering in the Vex Robotics competition. If you come to events here in Arizona, you'll oftentimes see me refereeing, and sometimes I'll have that blue flag cap there in the upper left-hand corner. I am currently pursuing a software engineering master's degree at ASU. And previously, over the summers, I've worked as an intern software developer at Optum, Garmin, and State Farm. So first, I want to start off with a note here. Making mistakes and fixing them is a part of programming. You're going to make mistakes. I might make some mistakes during this presentation, and I've been programming for a while. The thing about programming is it doesn't really matter if you make mistakes. It's all about learning the overall concepts and how to solve a problem. So if you forget the exact syntax for a particular programming thing or for how to make a motor do something exactly that you wanted it to, um, don't worry about it. It's more about learning the concepts. And I will say that the best way to learn programming is by just trying it. You can watch a lot of videos, you can watch a lot of presentations on programming, and honestly, it's a lot faster to try things out and break things, fix them, make it work. Um, so I highly, highly, highly encourage everyone to go ahead and experiment with this after they're done here. All right, so first we're going to start off with we're going to jump right into text programming. So just to review, code, whether it's block code or text code or any other form of code, is a list of instructions for a computer that it's going to follow in order. Um, it's going to wait until a command is done being executed before moving on. Now, we'll look at some stuff later on, but that doesn't necessarily mean it'll wait for, say, the motor to finish being moved, but it'll wait until one command is being done, which means that when we give that list of commands to the robot, it's going to execute them in order. So the order that we give them matters. Through these commands, we can instruct the V5 brain to move motors, retrieve sensor data, display screens and things on the screen, and so much more. We can instruct the V5 brain to, do autonomous routines to handle user inputs. It's our language for communicating with the brain. So we're going to be jumping directly into text programming with Python. Now, I want to make a note here real quick here. The reason that I'm choosing to jump directly into text programming is that text programming is not that much more difficult than blocks programming. The concepts are very similar in both ways. Both have loops, both have variables, functions, etc., which we'll go over. But Python and text programming in general is something you're going to see a lot more in industry, in real life programming, and in general, it's just a skill that's good to have. I I personally started off in block programming. I know a lot of people start off in block programming, but I highly recommend trying to make that jump to text programming as soon as possible because it opens up a whole new world for you to learn from. So yeah, we're going to be using a text programming language called Python. Python is available as a programming language to program Vex robots in VEX Code V5, which is a desktop application. The VEX Code Visual Studio Code extension, which is an extension for Microsoft Visual Studio Code, and the VEX Code Online website, which is the thing that I'll be demoing, but the syntax is the same for all of them. All right, so let's just go over some very basic Python syntax. Syntax is essentially just saying the format of our commands for the code. So say we have a motor called motor underscore one here. Let's say we want to make it spin in the forward direction at 100 RPM. We can use this following command to do that. We can say motor one dot spin and then open parentheses, forward in all caps, comma, 100, comma, RPM, close parentheses. Every single part of this statement is important. And it's important that we make sure that we type this exactly correct. Motor one is the name of our motor. If we misspell that or type that in, the robot's not going to know which motor we're talking about. If we say spin, spin is important because it's telling it the command on the motor that we're performing. This is generally called a function. So spin is a function of motor. Um, Forward indicates the direction that we want it to spin. So for instance, backwards is also a valid option here. 100 indicates how fast we want to spin, and RPM indicates the units. So in this case, we're saying we want 100 RPM. You could also say 200 RPM. You could say negative 100 RPM to spin the other direction. Forward, 100, and RPM are all called parameters. Parameters is something, a value that we give to a function to help it do what it wants to do. So for instance, spin is going to move the motor, but we need to tell it how it should move the motor, what direction. So we tell it forward, and we should tell it how fast. So at 100 RPM. So again, this syntax for telling the motor to spin forward at 100 RPM needs to be exact. There's a few different things you could do that wouldn't work. So for instance here, if we have motor one space spin and then forward 100 RPM, it's not going to work because it's not going to recognize spin as having been a function of motor one because there's no dot there. In the second list here, we've replaced the parentheses with brackets. Brackets have a different meaning to the computer than parentheses, so this also isn't going to work. And just double check something here. Yep. And on motor one spin here, we've missed a comma. So for some reason, now we're only passing two parameters here to spin, which is also going to be confusing. And it's not going to work. In motor one spin here, we've capitalized the M. So this is one thing, a concept that's also very important to recognize. Capitalization matters. So if we capitalize the M here, it's no longer going to be the same thing as lowercase m motor one. Uppercase M motor one is an entirely different thing, and it might not exist, or it might not do what we want it to do. So capitalization is very important. And then finally here, we're just missing parentheses entirely, which is just not going to work as we've seen before. Oh, and I do want to make one note. Feel free to post your questions or any comments you have in the chat or on the onlinequestions.org link. Either way, I'm monitoring both. And if there's any questions, I'll stop and I'll explain things. Please, this presentation is designed to be more of an interactive presentation. Unfortunately, we weren't able to be in person today, but please feel free to post questions in the chat. I'll be able to tune things to what you guys want to hear a lot more. All right. So one other thing that's useful about Python syntax is comments. Comments are basically just explanations that we can put inside of our program. So for instance here, we can put a pound symbol or a hashtag or an octothorpe, whatever you want to call it. And any text that we put on that line after that hashtag, after that pound symbol, is going to be basically ignored by the computer, which means that we can put information that's useful to us there. So for instance here, I've written motor1.spin forward 100 RPM, and then I have a little hashtag that says spin the motor. This way, as humans, we can make notes for ourselves right in our code to help us understand later on. As a programmer who's been doing this for a while, and I've worked on programs written by other people, sometimes even before I was born, comments are essential for helping yourself, for helping anyone else who's going to look at your code to understand it. A lot of the time, I found myself write some code, and then I'll come back the next day or the next week or even the next month and look at the code and be like, I don't know what this does. Because the code I understood it at the time, but it was something complicated and I didn't write it down. And then I have to figure it out all over again later on. That's not ideal. So I highly recommend that everyone who writes code should put comments in their code, explaining their code, um, even if you don't have other programmers in your team, just to do it to help yourself. All right, so variables are another important concept for Python. The syntax for variables is super simple. What a variable allows us to do is take a value, say a number or a piece of text or some other thing, and store it for later or for use somewhere else. So for instance here, oh, looks like we got some stuff cut off here. There's supposed to be an underscore there. Sorry about that. This is supposed to be my underscore variable. You cannot have spaces in variable names. So we have my underscore variable equals 352.4. And that will save that value of 352.4 for later. And same deal here, my underscore variable underscore 2 equals hello. And we have either single quotes here, or you can also use double quotes sometimes. In this way, we're storing text. So it's really simple. You just type a name of a variable that you want it to be able to refer it to as later, and you set it equals to whatever you want it to be equal to. Um, we can also do math with variables. So for instance, here we can set variable. Oh yeah, it looks like they got cut off, unfortunately. Variable underscore one, variable underscore two, variable underscore one equals 3, variable underscore 2 equals 6. And then we can do variable underscore 3 equals var1 plus 1 minus var2. So in this scenario, var1 is 3. We're going to add 1 to it. So then that value will become 4 here. And then we're going to subtract 6 from that. So 4 minus 6 is going to be negative 2. The value of var3 is going to be negative 2. We can also use variables as parameters in place of pure numbers. So for instance here, if we want to we have a variable called speed, and we set it to 93, and see we're using our comments here to explain what we're doing. And same here, we're also having some comments to explain some stuff. We call our motor1.spin function again, but instead of having RPM be just a pure number that we enter directly into the function, we set it to speed. In this case, the motor is going to spin at 93 RPM because the value of the variable speed is 93. All right, so that is some of the basic Python syntax. Now let's think, especially commands. Now let's think about some stuff that's higher level than command. Sometimes there are different scenarios that we want to account for. Sometimes a button is being pressed, sometimes it's not being pressed. And we want to do different things depending on whether it's being pressed or whether it's not being pressed. So this is called a conditional. And we can do conditionals with what's called an if statement. An if statement syntax is the following. We can have an if followed by a condition, colon, and then a tab. This is extremely important. We have to have this tab here. And then we can do something with that. So in this example here, we have if bumper, bumper underscore a. Looks like, I'm sorry, some of these underscores got deleted, unfortunately. If bumper underscore a is dot pressing. So basically, if the bumper is being pushed, do motor underscore one dot stop. So in this scenario, if the bumper is being pressed, stop the motor. Otherwise, which is what this else statement means, else means if this wasn't true, so if we're not pressing, else, colon, spin the motor forward at 100 RPM. So in this way, we can use a button, we can link the value of a button or a bumper or a limit switch or whatever to the behavior of our motor. And this is something that can be done in one go. So one thing I do want to call special attention to, and I mentioned it before, is see how the motor statement here, motor underscore one, starts in a few spaces. That's because when you have an if statement or an else statement or something like this with a colon, and there's code that's supposed to run if that statement is true, then you need to indent it. So you need to press tab on your keyboard, and that is part of the Python syntax. If the code is not indented, say if motor one started over here, just on the same level as if, it would not run if the button was pressed. So that's an important part of Python syntax. Um, Conditionals can also be chained together, so we can check for a few different conditions at the same time. or sorry, in sequence, my bad. So for instance here, we can check to see if bumper A is pressed, um, then stop the motor. If it isn't pressed, but bumper B is being pressed, we can spin the motor forward at 100 RPM. Or say we could even replace this, say, backwards. We could spin the motor backwards if bumper B is being pressed. And then we have else. If no bumper is being pushed, motor 1 spin forward at 100 RPM. So in this way, we can have different scenarios for, we have different behavior for different scenarios of our sensors. Another logical structure in Python is loops. So sometimes we want to do stuff repeatedly. For instance, often we will want to, especially in driver control mode, we'll want to repeatedly set the behavior of motors based off of our joystick values on our controller, or if we're pressing buttons on our controller, or if there's bumpers pressed on our robot, etc. So we'll repeatedly, in a loop, constantly update the values of the motors. So one way of looking at a loop here is the syntax. So we can have while bumper A dot pressing. So it'll be while some condition is true, repeatedly execute this code in order. So while the bumper A is being pressed, the robot will print pressed, and then it will wait 1 second. Sorry, 0.01 seconds, which is 10 milliseconds, which means that 100%, 100 times a second while bumper A is being pressed, it will print pressed to the console. Okay. So, all right, let's try this out in VEX code. See here, come on. Okay. Well, okay. So, in VEX code, let's pull up VR. You know, actually, let's pull up a blank one real quick here. I had one demo figured out here, but let's pull up a blank one real quick here. So VEX code VR, let's discard it for now. Where is virtual skills? There it is. Cool. So VEX Code has a few different options here. There's a normal VEX Code v5, which is something that you would use to program your robot. It looks very similar to VEX Code VR, but the reason I'm going to be using VEX Code VR instead here today is because VEX Code VR allows us to have a little virtual robot that we can drive around and program. So because it's a little bit difficult for me to show you like a physical robot here, we're just going to program this virtual robot today. The code is very, very, very similar. All the commands are going to be basically the same. So for instance, here we can take a look. The robot, we have a little robot here with a tri-ball on a virtual model of the spin-up field. And this is actually, let me just make this a little bit bigger. The cool thing about VEX Code VR is that there's also a virtual skills function, which is actually what you can see where we're in right now. Teams can program this pre-built robot here to score points within the simulation, and they can submit that score to a global leaderboard and win prizes. I don't remember exactly what the prizes are, but this is a competition that you can do from home if you just want some more programming experience. So let's start off with some basic. Oh, you can't see the screen. Oh no. Let me try that. Thank you. Thank you for that. Yeah, we're gonna get the screen capture fixed here. 1 second. Alrighty. Okay. Sorry about that. Thank you, Daniel. I was not aware that that was not showing. Okay, so thank you. So, I'll go through that again. Hopefully this is working now. So this is VEX Code VR, and there is the VEX Code V5. It's a little bit of a confusing name, but this is what you would normally use to program your robot. You see, there's a controller you can download and build, and all that fun stuff. VexCode VR is basically the same coding, but there's a virtual simulator here in the spin up. Sorry, not spin up. In the over under field here, and we can score the simulated try balls in the goals for points. So we have this little robot here that we can program to drive around. So for instance, here we have this default program to tell the drivetrain to drive forward 200 millimeters, and we can go ahead and run that actually. You can see the drive move forward 200 millimeters. If we stop that, we can reset everything, and we can go ahead and change this here. So if we go ahead and do stuff like, let's just say drivetrain dot, let's see here. Will you turn? Yes, turn. We can do say turn right, and then we can say 90 degrees. And then let's go ahead and reset. Right? And we can see our robot drives forward 200 millimeters and then turns right 90 degrees. So in this way, we can see that the commands are executed sequentially. So it waited until it finished driving forward 200 millimeters before it started the turn. There's an order to our actions, and we can adjust these values here in the code. Let me see here if I can make this a little bit bigger. There we go. Okay, that's not too big. Okay, cool. Yeah. So, and there's a bunch of different ways, a bunch of different commands we can use to do this. So for instance, here on the left-hand side, which is also present in the normal VEX code, there's a list of all the commands. So for instance, if we want to look at the drive for command and learn a little bit more about it, we can click this question mark here. And this question mark brings up a lot of information. It'll give you some examples on how to use it. For instance, here we can even switch into inches. Let's hide this real quick. And it will give you information on the syntax for it. And we have a bunch of different things here. So for turn 4, stuff like that. It's pretty cool. And same deal for motors, brains, looks, events, etc. We also have stuff like our loops. So we have a for loop, we have a while loop, we have if statements, if else if, etc. Like what we talked about in the slides. Sorry, I have 2 keyboards here. So yeah, VexCode VR is a great tool for learning the basics of text programming, especially at home. So you don't have to be in the lab or with a robot trying to figure that out. But once you're ready, you can go ahead and move to normal VexCode V5. And a lot of the same stuff is there. So let's walk through setting up a drivetrain device, for instance, here. So by default, you'll see the drivetrain isn't really here. That's because we haven't configured one. So let's go ahead and do a 4-motor drivetrain. You know what? Sorry. Yeah, let's do a 4-motor drivetrain. So for instance, here, we can actually tell VexCode whether which motors are plugged into what ports. So we have 2 drivetrain motors on the left. So we'll say they're plugged into ports 1 and 2. And then it will ask us which ports are right-hand motors. So we can say let's plug those into ports 8 and 9. And then we can say whether we have a gyro, a GPS sensor, or an inertial sensor. And that will be used to assist with rotation of the robot. So let's just say we have an inertial sensor on port 5. Then we need to tell it our wheel diameter. This is important because larger wheels are going to make our robot move further. So if the wheels are smaller, then it needs to tell the motors to spin less distance. And if the wheels are larger, then if the wheels are smaller, it needs to tell the motors to spin more distance in order to move the same distance as a robot. And if the wheels are larger, the motors don't need to spin quite as much in order to get the same distance. So we're just going to stay with standard 4-inch wheels. That's just your standard Omni wheels that you get in the kit are going to be 4 inches. And then our gear cartridges, let's just say we have green motors, or sorry, let's say we have 200 RPM motors. That's a bit funny. They have these a bit backwards. Generally green is 200 RPM and red is 100 RPM. Oh, sorry. That is actually green. I'm colorblind. I'm sorry. Green and red is hard. All right. So now we have a drivetrain. And surprise, on the left-hand side here are all of our drivetrain functions have popped up. So we can even actually drag these in from the left-hand side. So if I click this and drag it, bam, we have a drivetrain to drive for 200 millimeters. And we can just go ahead and edit that. We can say, let's say we want to drive forward for 20, and we go over here to millimeters, inches. And when it does like a little suggestion like that, so like when I start typing capital I, capital N, I can just hit enter and it will autofill inches for me there, which is really, really nice. All right. So I think we're going to return to the slide deck here. Let's see here. Programming, cool. All right, here. All right, so introduction to version control. So the other part of programming is what you need. What do you do with the code once you have it? And how do you collaborate with other programmers in your team? So a lot of teams have more than one student doing programming. Sometimes you'll want to save that code for, the programmer that's going to be the team next year, or maybe the programmer from last year, wants to give you some code. What's the best way of moving this around? I remember back when I started, I had a flash drive that I put my code on. But the question was, well, what happens if I accidentally drop the flash drive, or if I leave it somewhere, if I lose it somewhere? Then all of my team's autonomous routines, all of our code is gone. And that's an issue. So um, there's sometimes we moved over to something like Google Drive, but the issue with Google Drive is if you have multiple people working on the same piece of code at the same time, then you can end up with conflicts. Even if they're like, say, like they're working on different pieces of code in the same file, that are like totally different parts of the file. If they're working on the same file of code, then there's going to be conflicts, and it's going to be really hard to kind of merge everyone's changes. And that's just annoying to deal with. So there's a better option. That option is called Git. Git is what's called version control software. It is software specifically designed for software development, for code, and for tracking the changes made to that code. And it can be used because it tracks those changes. It can help merge any conflicts, any conflicting changes you have with someone else. Git allows you to create branches, and branches are kind of like a separate list of changes from the main list, which allows you to work on a change. So one really common thing that you can use these for is say you want to develop an autonomous routine for a particular thing, or say a programming skills routine, or even say you want to make a little change to the robot's code so that we can use encoders instead of the inertial sensor, or something like that. But the other programmers in your team still want to keep on working on the autonomous routines for the upcoming tournament. So what you can do is you can make a branch off of your main branch or master branch on the repository, and you can do all your work there. And any work you do on that other branch won't affect anyone who's working on master. So you can see here, up here, you've made a branch and you're committing, you're making these changes, but it's not affecting anyone here until you merge your changes into master. So at that point, then you can take your changes along with their changes and combine them back again into one continuous line again, which is a really nice way to develop changes. So for instance, while you're making changes, while you're trying to do things and things are kind of broken while you're working on them, you can have them exist in this other branch where it's not going to affect everyone else, and you can figure it out. And then once you figure it out, you can combine your work again using Git. GitHub is separate from Git. So it is not, Git and GitHub are not the same thing, but GitHub uses Git, if you can think of it that way. GitHub is a website for hosting Git. Git is by default a local thing. It only really runs on your computer, but GitHub allows that Git instance to run on the internet. And you can host Git projects called repositories, and that kind of acts as a backup for everything. This way, you can have multiple programmers working on the same GitHub project, um, and they can all share the same code. So everyone can be what's called pushing their code to GitHub. That means you're taking the changes that are on your local computer and you're pushing them into the internet. You're putting them on the internet on GitHub, which can be private. So to be clear, they're not necessarily a public repository. So you don't have to keep all your code public, but that allows you to share with other people on your team. So when someone makes a change, they can push those changes to GitHub, and then what the language is, the other person can pull those changes from GitHub. All right, so um, I can go over some Git features here. There is a GitHub desktop app. Let me actually just pull that up real quick here. Let me see if I can get some pictures here, because GitHub desktop is really cool. You can see here that like it lists out the changes that have been made to some code. For instance, here this has you've added a comment here, and this is a different language from Python, so don't worry about the code. But you can see here that it lists which changes have been made at what time. And you can even see changes over time. So for instance here, if you had a piece of code that worked a certain way a few months ago or a few weeks ago or even a few days ago, then you can go back and look and see exactly how that code was. So this way, you don't have to be afraid about deleting code, which is really nice. A lot of the time, if you don't have version control, if you're just working off of one version of a file, then you kind of have this, you'll like comment out code or put it at the bottom of the file so that you want to keep it for later because maybe you'll need it later, but you don't want to use it right now. And it kind of ends up being this really ugly grouping of code that's dead that you don't want to use. So Git can help you with that because you can just go ahead and delete that code, but you can go back in history and see what that code looked like. You can go back in the future and look and see what that code looked like, which can be really great. So let's look at the GitHub history for my team, Pyro's uh, Git repository this last year. So we use something other than VS Code. We use something called Prose, which is a little bit more advanced programming environment. So don't worry about like understanding what the code does. I just want to show you what Git commits look like. So you see here we have 6 branches here. We have a branch for we're doing some pure pursuit, so we call it follow code. We have some cubic drive mapping, and we have some integration with some sensors that we did. So if we go to this branch called follow code, we can go ahead and look at the commit list. And here we can see all these changes. So for instance here, we can see, oh, oh, hi, Ion, I see that. um, we can go ahead and like look and see what the changes are. So for instance here, let's see here. Here I retuned some of the heuristics we had. So we can look here and it see that in the file main.c++, this is one file here of changes. We can see that I changed this number 43 to 1100. We can see I changed uh this I commented out this line and added a new line, and you can just scroll through these list of changes here and see exactly what was done, when it was done, and who did it. So you can see even the person who made those changes. So um, one of the features of Git is you can actually look at a particular line of code. You can say who wrote that, and you can actually do a command in Git or even the Git GitHub desktop to see who wrote a particular piece of code or who last changed it, and it'll tell you exactly who that is. And more often than not, when I'm going, who wrote this code? It's me. More often than not, I'm the one who wrote the code, but this way you can find who wrote the code, who you need to talk to understand it. It is used. In my work at State Farm and at other places, we use Git extensively it is the industry standard, I would argue, for multiple programmers collaborating, for keeping track of your changes. Every bit of code that I personally write, I put into Git, just for version control and for just general usage. It is extremely important to learn, and I highly recommend. Uh, I highly recommend every team that does text programming use Git in some way. So some miscellaneous tips. So one thing I do want to say is that for Vex Code, the especially if you're going to use Git, these are the online versions here, which are really easy to access, especially if you want to use them at home. But if you want to use Git, I highly recommend using the Vex Code Visual Studio Code extension. Um, which let's see here. Yeah, there we go. Which allows you to write code in a little bit of a different looking place. But Visual Studio Code is a text editor for writing code, that is very commonly used in the industry. Um, I use it at work all the time. But this extension allows you to do is to use Vex code functions and stuff to control your robot inside of Visual Studio Code. And from that, you can actually just have your code in normal files, which can go into Git very well. So I recommend looking into this once you've got kind of the basic hang of Vex code in the browser here or on the desktop. All right. Okay. Let's talk about some miscellaneous tips here. So, one thing I wanted to talk about was that, as a referee and as someone who has done programming in Vex for 10 years now, just want to kind of call out some common issues I see with teams and their code. Um, so in a lot of years, you'll want to see, like sometimes you'll have different uh, programming or autonomous routines, depending on which side of the field you're starting on, especially this year, or depending on what your partner can do, or maybe you have a secret autonomous you reserve just for eliminations to catch your opponents by surprise. And a lot of the time, I'll see teams make entirely separate versions of their program. So you can actually download like 8 different programs to your brain, and what I've seen teams do is they'll make a separate program of a separate version of their program, download it to their brain under a separate slot, just to have a different autonomous. This isn't something that you need to do. There's a lot easier ways of doing this. So, for instance, here, um, the most basic way here is on the right, where you can just have a potentiometer connected to an axle, and then you have like a gear or some other like thing, and it basically looks like a clock where you can just spin this to different locations at the beginning of the match before the match starts. And then in your code, check the position of the potentiometer or of the whatever sensor it is you're using, rotation sensor, the new potentiometer, or old potentiometer. Either way, check the position of that potentiometer, and then depending on where the potentiometer is spun to, run a different autonomous routine. So I know some like going thinking back in my mind, back in like Turning Point, there were you had to shoot balls at the flags, and sometimes depending on which uh, autonomous my opponent had, I wanted to switch my autonomous to react to theirs. So right before the match starts, so I don't have to re-download my code. I don't have to start a different program. This is faster, and it's sometimes even a little bit more discreet because my opponent doesn't necessarily know which autonomous I'm choosing. I can turn that dial to whichever autonomous I want. So sometimes I'll like put marker on, say 1, 2, 3, and then I know what autonomous 1, 2, or 3 does. Now, if you want to get a lot more fancy, and make something a lot more nicer to implement with, you can build a custom screen and custom buttons and everything for the actual brain screen itself. So you can get commands, and I'm gonna go show some stuff real quick after I'm done with this, in Vex Code how you can do this. But you can make buttons on the screen, you can make text and graphics and all these things, and through that you can make this little menu system where you tap on the brain to select exactly which autonomous period you want. Sorry, which autonomous you want your robot to run, which can be more complex, than just turning a dial. It takes a lot. It takes a bit more work, but it's something that can be flashy and can be impressive to the judges and can allow for more complex behavior. I also wanted to, actually, before we go into that, let's go back to VEX Code real quick here. So let's see here. So yeah, we can print some stuff to the screen with stuff like this brain.screen.print and stuff like that. We can draw rectangles and all these different shapes on here. I'm trying to find where here we go. We can do things like brain.screen.pressing. So for instance, this will allow us to detect if the brain is being touched by a finger right now. So we can do stuff like that, like run that in a loop or whatever. Let me get rid of this here. And that way we can check to see if someone's touching the screen. We can also do things, and then we can do stuff like get the X position, get the Y position, and we can store these in variables, say, and then say we can say, if the X pause is greater than 500 or is greater than 50, uh, and then inside of that we can do if Y pause, whoops, see, I told you I might make some mistakes, is also greater than 50. So we can say if we're away from that corner, then we can do brain.screen.print something like that. So in this way, we can check for touch events, and we can start to kind of construct a GUI for what's called a GUI. It's called a graphical user interface for pressing buttons and doing things like selecting autonomous and stuff like that. So VEX Code will help you with that, and it will even give you some let's see here, some explanations of it, and like how to do it. So see, for instance, here we have columns, and that's how it'll tell you the position. So the VEX Code help is actually really good. In previous years, it wasn't so good, but in recent years, they've definitely upped their game, and there's a lot of really nice examples, explanations of how things work. So I highly recommend using some of the VEX Code help stuff to help you understand how everything works if you have any questions. And also just experiment. Try it out on your robot. See what happens. You're not going to be able to break the brain. You're not going to be able to do any permanent damage. It's code is one of those things where, you know, if you're a mechanical engineer and you're trying to build a car, it's difficult, to just build a bunch of different cars and see if they work, right? That's expensive, that's hard, that's time consuming. But with code, we can just try a bunch of different pieces of code, a bunch of different changes, and try it really, really quickly and see what happens. And that's one of my favorite things about code. It lends itself really well to just trial and error and experimentation. Oh, I see your comment, Ion. Yeah, yeah, I know that they didn't have this for a few years, so it's really great that they have this help now. Um, it makes it a lot easier to learn things. All right, and I think we're coming up close to the end here. I think that's all I got for prepared stuff. I can take any questions that are in the chat. I have plenty of time here, so if anyone has questions, feel free to post them in the chat, or on that questions page. Let me pull that up again real quick here. Cool. Yeah. Um, the chat works or here if anyone has any questions. Otherwise, that's the end of the presentation. Thank you for listening, and I'll sit here on for a little while and see if there's any more questions. Oh, I see that question from you, Ion. Let me look at this here. What resources? So the question is, what resources would I recommend for learning C and C++? Um, the tricky thing is C and C++ are complicated languages, so it's going to take some effort. But I would recommend um, learncplus.com is a really good uh, recommendation. So let's see, learn.com. Oh, that's not what I wanted. Whoops. And there's a bunch of tutorials here. So for instance here, and it explains a lot of the background stuff. So you need to understand what compiler is, what integrated development is, and stuff like that. Some of this is a little bit lighter because like Vex code will kind of will help you through that. It doesn't really make you set up the compiler and stuff like that. That's really annoying and hard to deal with. Um, but it gives you a lot of the basics of like C++ here. So we can see some basic C++ programs, which you can see looks quite a bit different from Python, but ultimately you'll find a lot of the concepts are the same. So if we look at stuff like, let's see here. They have variables, stuff like that. Where is, let's see here. I'm trying to find here. Control flow. Okay, so like, so for instance, like they have if statements and stuff like that. So we have that same kind of if condition, um, true, else, etc. It's just done a little bit differently. And that's fine. There's a lot of different things that are valid. But in C++ has a lot of the same concepts, variables, like I said, but it's just more complex. There's a little bit more difficult to syntax. So for instance, you'll see there's a semicolon after every line. Um, there's this double colon thing here. You'll see STD, which means standard, prepended to a lot of functions. Um, and there's some other, things like include and stuff like that. Learn C++ is a good resource to kind of understand the basics of C++. Once you've gotten a little bit of the basics, you don't have to go too far. Then Vex code can help. So for instance here, let's just do a new one here. New text project, discard, and get rid of that. And we can actually do C++ Vex code in the browser even here. So we can see we have a little bit of a different thing here, but it still has all of our same commands that we were looking for here. So we can set up a motor, let's set up a motor. Let's do 1.1. Here we go. All right, so now we have motor.spin, and we can do the same thing that we had um, in Python, but it's a little bit different here because it's C++. And the Vex code API specs will help you with that. I believe there's also help for that. Yep. So there's, you can see there's some examples and stuff like that. Um, it'll help you figure out what you need um, uh, for each command. It's a little bit harder to learn, like I'm saying, but it can be rewarding. So C and C++ are also very commonly used in industry. I know Python is um, as well, but they're both common languages. C++ is just a bit more complex. If you're interested in moving to something like prose, though, which is what like if you're interested in more advanced programming, I recommend taking a look at prose. Let me pull that up real quick here. Which is a actually community developed programming language by the Purdue Robotics team, which would be BLRS, and they have their own kind of C++ programming environment, which allows you to do some more advanced stuff and is in general just nicer to work with if you're an advanced programmer. All right, Daniel asked a question. Overall, would you recommend Visual Studio or the free browser for a team with a mix of new and veteran members? I think in that scenario, I would recommend the Visual Studio extension. Um, because uh, if you want multiple teams to, sorry, if you want multiple students to work together, you're going to want to use Git. And Git is a lot. You can use Git with the Vexcode v5, but it involves kind of downloading the program every time you make a change and putting it on your file on your computer. And it's not as seamless. Um, and also I'd say for veteran programmers, it's going to be more frustrating to use. They're going to feel start to feel limited by VexCode. So for instance, VexCode only is going to allow you to have like one file, which is totally fine for beginner programmers and for basic programs, but it becomes start limiting. So I'd recommend using the Visual Studio extension. The only downside is that, as far as I know, the Visual Studio extension doesn't have some of these help things built into it. However, you can always have this running on the side, which is a lot of things that I will do. So, for instance, with Prose, I'll have a web browser open to the Prose help while I'm programming Prose, so I can browse through that. You can have VEX Code open in a web browser just to look at the help, so that you understand how to use things. And it also has its own kind of autocomplete that's even better than VEX Code's here. But yeah, overall, I would recommend using the Visual Studio extension if you have a mix of new and veteran members. That way, the veteran members are also going to be able to help the new members get up to speed with Visual Studio. The actual code that you write is the same, whether it's, you know, the online or Visual Studio or the desktop app or whatever. If the actual code and the syntax is all the same, so you can actually copy paste code back and forth. It's just easier to use and a bit nicer for the advanced students if you do Visual Studio. And again, if you have multiple students, it's a lot easier to use Git with Visual Studio. In fact, as far as I remember, Visual Studio actually comes with Git integrated into it, so you don't even have to leave Visual Studio to use Git, which is really nice. I hope that answers your question, Daniel. I'll wait a few more minutes here, see if there's any more questions. All right. I think that's going to be it then. I don't see any more questions. Um, thank you all for attending this. It's been great having you guys. And we're going to send out the slide decks, I believe, and the recording will be of the presentations will be available on the 18 by 18 YouTube channel as soon as we turn it off here. Thank you for attending, and hopefully I'll see you guys throughout the season.